Hey guys, let's talk about the time-dependent charging equations. Now, rather than give you all of the equations at once, I'll give them to you one at a time and describe their utility and talk a little bit about the shape of the graph that you might get out of them. So this one right here, as you can perhaps understand, is the charge versus time equation for charging a capacitor. So it's the charge on the capacitor as a function of time. This is what's called a natural growth. Natural growth is, oh, that's maybe the ugliest I've ever drawn. Don't worry, we'll use Desmos a little later on, and you'll get to see what a pretty one looks like. But the idea is that it's coming up to some maximum value. It asymptotically approaches it. And the value of that maximum, just like for any of these equations we're going to see, is right here, which you may remember seeing that moments ago. That was labeled as Q max. The voltage on the capacitor is given by a very, very similar equation, which it shouldn't be surprising at all that this is what it is, because if you do Q divided by C, you get the volts on a capacitor. That's what has happened here. If you take the charge equation and divide it by C, there we are. It's now the volts equation. Now, the current equation, there's not necessarily any great way to get it other than to take a derivative, and I really don't need you to understand how to take a derivative here, but it would be the derivative of the charge equation if you happen to be in calculus. And again, a common feature of all these equations, the sort of lead coefficient here represents the maximum value. So if you think back again, like a minute ago, well, 5 minutes ago in this video, I said that was the maximum current. There it is at the front of that equation. Now, the difference between the exponential decay, which is what this one is, and the natural growth function has to do with when they reach their maximum. With exponential decay, you hit the maximum at t equals 0. That's when we have the maximum. Anytime later than that, and since it's a decay, it's going to decrease. For the natural growth equations, like these two, the maximum value is reached much, much later, okay, like an infinite amount of time later. Finally, we have the equation for the volts used by the resistor, which this is just V equals IR. Okay, multiply the current equation times R, and there you have the volts equation. Now, you'll notice all of the equations have this RC thing in them over and over and over. That is referred to as the time constant. And it's represented by the letter tau, and has the value RC, which somehow works out to be in units of seconds. Believe it or not, somehow, if you take an ohm times a farad, you get seconds. But it is important to know the role that that time constant plays in functions. So later on, when we look at the shape of graphs, you'll see how important the RC is for determining how quickly a function grows or decays. And frankly, sometimes they won't even tell you R and C individually. They'll just tell you the time constant is 2. Have fun with that. All right? And as long as you know what RC is, you don't necessarily need to know either R or C, such as if you were trying to do something like determine the volts on a resistor at a particular time. Now, what about discharging a capacitor? So this would be, now we're starting with a charged capacitor. Discharging it would look like moving the switch to that position so that now current can begin to flow around this little loop right here. And notice that the battery is cut out from this. So if you were thinking, how can current flow if the battery is cut out? Like batteries make current. Well, so do capacitors. When they are discharging, a capacitor acts like a battery. Ever so briefly, it will push current around your circuit. So effectively, it takes the place of the battery in this very tiny little circuit over here. The direction of the current during discharge might be a little bit confusing at first, but if you think back to earlier when we were charging it, current was flowing basically this way. And we said the left side of that capacitor was the positive plate. Well, with a battery, current flows from minus to plus. A discharging capacitor will do the same thing. And so the direction of discharge is the opposite of the direction of the current during charging. So the direction of the current during charging was this way through the capacitor. As it discharges, it'll go that way. But we are going to get, again, a time-dependent set of equations where the charge on the capacitor won't remain constant. And the reason, of course, is what's happening is these pluses are trying to get back to these minuses on the other side. Well, as a plus moves around this way and neutralizes a minus, well, now there is less charge on the capacitor. And so that means that this term here for the volts on the capacitor is going to keep getting smaller and smaller. The capacitor is the thing that is making the current happen. And so as the volts on the capacitor decrease, the current will decrease as well. So when we are discharging a capacitor, everything is going to be exponential decay. There's no natural growth here. It's just decay, decay, decay. So in simple form, as it discharges, Q goes down, so the volts on the capacitor go down. And as the volts on the capacitor go down, the current must decrease as well. So all of the time-dependent equations for discharging are going to take the form of exponential decay. This is the one that we'll use for the charge as a function of time. There's your initial charge, whatever that may happen to have been, and there's our exponential decay part of it. Same idea here, volts on the capacitor as a function of time. And here we have the current as a function of time. And finally, just simply the observation that the volts used by the resistor in this circumstance is the current equation times the resistance, which if I were to plug in this thing from above and then multiply by R, I think you would see that it would just turn into VC all over again, which reflects what I said earlier. In the very simple loop equation we wrote, we showed, hey, the volts on the capacitor and the resistor are equal at any particular moment. So let's look at some graphs of those time-dependent charging equations that we've looked at. And then we'll also look at the discharging ones for that matter. And at the moment, I'm graphing these two equations. This one here is equipped with a slider in it so that I can change the value of it. We'll talk about exactly what I'm doing when I slide that around in a moment. What I want to highlight to you is the highlighted equation here. What I'm graphing is going to be explicitly the volts on the capacitor versus time. So this equation is of the same structure as this one, with the exception, of course, that I can't make the x and y axes be whatever I want. This should be the volts axis, and then instead of an x, it should be a time. Okay, but whatever. The 9 here, that represents the EMF of the battery. So this would be the volts on the capacitor versus time, where it's connected up to a 9-volt battery, and the time constant is 1 second, if you recall what a time constant is. And remember, you calculate the time constant using tau equals RC. Okay, so if this is the basic shape of this graph right here, and remember that's called a natural growth function, I can generalize that to any RC circuit I want, where the only difference really is going to be the maximum voltage and the particular time constant. All right, now let's mess around with the charging voltage. Suppose I hook it up to a 12-volt battery. That's it. That's the difference, right? It goes up a little bit higher, but it's the same basic shape of graph. Now, if I mess around with the time constant by saying increasing the resistance or increasing the capacitance, what effect does that have? Well, if I increase the time constant, you can see the final voltage is still basically going to be the same, but it takes longer to get there, right? At any particular moment, the charge and therefore the volts on this capacitor, or well, the volts on the capacitor is going to be a smaller amount if we have a larger time constant. All right, if I make it be less than 1, then it charges quicker, right? So it's, in this case, almost immediately up to the maximum volts of 9. What about the volts on the resistor? That would be this equation down here, okay? The volts on the resistor, you can see follows an exponential decay graph. So that would be the purple one that I've graphed out here, or this right here, again with a time constant of 1. And please note that at any particular moment, if you pick out any two values on this graph, on the two graphs rather, and add them together, they will add up to 9. So implicitly what I'm doing here is I've got a simple RC circuit where they are connected up to a 9-volt battery. Initially, the volts used by the resistor looks like it's 9. That's because initially the capacitor has 0 volts on it because it has 0 charge. So therefore the resistor is using all of the volts. Sometime later, let's say this moment, at this particular moment, the volts on the capacitor is 2. If I go up and look at that exact moment, okay, on the resistor graph, it's 7. Well, 2 and 7 make 9, and that still works out. So pick any two pair of values, this one here being particularly interesting, 4.5, 4.5, they're using the same number of volts. Pick any two values on here at some moment, and they will add up to 9 because that's the charging voltage. The other thing of interest is, I'm going to graph those same ones but with a slider. If I have a smaller time constant, you can see the volts in the resistor goes shoo down really fast as the volts on the capacitor goes up really fast. Okay, so changing the time constant, right, they still coordinate, right? So the volts used by each one are still going to be adding up to 9 and change proportionate to the time constant. Not going to graph out the discharging equations because it's not nearly as interesting. Because if you recall, what you should observe from all these is the exponential decay graph. Okay, so the two basic shapes that you got to know. You need to know your natural growth. You need to know exponential decay. And you need to know what those things are for. Resistors almost always are going to look like exponential decay. The capacitor is going to look like natural growth. This is during charging. During discharging, what you will always see for everything is going to be the exponential decay. And you also ought to know the effect of changing the time constant. A smaller time constant, because of having a smaller resistance or capacitance value, means faster charging. It gets all the way up or all the way down quicker. If you have a larger time constant, then it takes more time to either charge or discharge or do whatever it's doing. All right, that's the basics of the RC circuit graphs. I hope that was informative. Thanks for watching, guys.